You may wonder why Yoneda's lemma is referred to as a lemma rather than a theorem, even though it's such a famous and important result of category theory. One of the reasons for this is that it has so many striking and important corollaries that even though it's an interesting result on its own, because it has so many important consequences, we can kind of think of it as more of a stepping stone to all of those consequences. Stepping stones in proofs are usually known as lemmas, sort of intermediate results, so that's why Yoneda's lemma is called Yoneda's lemma. We're going to look at 3 of the important consequences of Yoneda's lemma. The first one being that there is a contravariant embedding for any small category C into the functor category going from our category C to the category of sets known as set superscript C, and we'll recall the definitions of all of those. 2 is that any 2 objects, A and B, are isomorphic in a category C if and only if their contravariant home functors, home blank A and home blank B, are also isomorphic. And home blank A and home blank B are both functors going from category C to the category of sets, and so they also live in this category here, set superscript C, the functor category. And finally, we'll see that Cayley's theorem can actually be thought of as a consequence of Yoneda's lemma. So obviously, historically, Cayley's theorem came first as a very important and foundational result of group theory. So we can kind of think of it the other way around, that Yoneda's lemma is a generalization of Cayley's theorem, but we'll prove it the other way. We'll prove that Cayley's theorem can be proven using Yoneda's lemma. So to prove the first result, let's first recall some of the definitions required. The first one is an embedding. So an embedding is a type of functor, in this case a contravariant functor, which is full, faithful, and where the object mapping is injective. So recall that full means that when the home sets get mapped, they get mapped by surjective mappings. Faithful means that when the home sets get mapped, they get mapped by injective mappings. Therefore, full and faithful together mean that every time a home set gets mapped by the functor, it's a bijective mapping. We can assign one-to-one relationships between the morphisms between 2 objects in the domain category and the morphisms between 2 objects in the codomain category, and where the object mapping is injective. Next, we recall the definition of a small category. So a small category is simply a category where the objects together form a set. That is, the objects together do not form a pure class. Finally, recall the definition of set superscript C, which is a category where the objects are all of the functors going from category C to the category of sets, and the morphisms are the natural transformations between any 2 functors. So if the objects are functors, then the morphisms between them are natural transformations between those functors. This makes sense because natural transformations are closed under composition, and so if we compose a natural transformation with another natural transformation, we get a natural transformation, and therefore composition makes sense within this category. One quick note here on why C needs to be a small category in this case. When we define this category, set superscript C, we need to have that the morphisms are natural transformations between functors. And we've defined categories in such a way that home sets must be sets. That is, the natural transformations between any 2 functors must form a set. But this may not be true for arbitrary categories. Arbitrary categories could have pure classes as the collection of natural transformations. So in this case, we need to restrict C to be a small category so that these sets of morphisms will actually form proper home sets and never home classes. So, combining all of these definitions together, what we need to show in order to establish this result is that for any small category C, we can create a functor, call it y, going from C to the functor category from C into set, where all of the home set mappings of the functor are bijective, and where the object mapping of the functor is injective. So to prove this, let's fix a small category C, and let's define the functor y, which is a contravariant functor, going from C into the functor category from C to set, defined by the following. Well, if we map an object of C in C, we need to get a functor from C into the category of sets. Well, we know the contravariant home functor is one of those. The contravariant home functor home blank C with target object C is a functor from C to set, so it will be an object of this category. And if we have some morphism F going from B to A in the category C, then what does this need to map to? Well, it needs to be a natural transformation going from home blank A into home blank B. It's a contravariant functor, so the order here needs to be flipped, and we apply this mapping to the objects of the domain and the codomain. And here's where we can apply Yoneda's lemma. We know that there's an exact correspondence between the objects in the home set from B to A and the natural transformations between these two home functors. So we can simply use follow by F applied to any domain which is in the image of this functor. So basically any domain where you're looking at a home set going from some object into A, and we can apply follow by F to all of those, and that will give us a natural transformation. So this should be a well-defined functor according to the Yoneda lemma. Well, first it's easy to see that this mapping is injective, because if C and D are two distinct objects in our category C, then these two home functors must be different, because this home functor, home blank C, is a whole bunch of morphisms which all have the same codomain C, and home blank D would be a whole bunch of morphisms which all have codomain D. So clearly those are going to be different if the objects C and D are also distinct. Next, we know that this is bijective directly because of Yoneda's lemma. We know that there is exactly a one-to-one correspondence between the elements in the home set from B to A and the natural transformations going from this home functor to this home functor. Well, that's what we needed. We needed an injective mapping for the objects and a bijective mapping for the home sets by this functor. And so we can see that this functor here is an embedding from C into the functor category from C to set, which is called Yoneda's embedding. And that proves the first result. So we'll actually use Yoneda's embedding to help us prove our second result, which is that A and B, which are both objects in C, are isomorphic if and only if the contravariant home functors home blank A and home blank B are also isomorphic. So to go this direction, first suppose A and B are isomorphic. Well, then there's some isomorphism F going from B to A as well, namely the inverse of whatever this isomorphism is. And we know that thanks to our Yoneda embedding, y of f is going to be an isomorphism going from home blank A to home blank B because functors preserve isomorphisms. So because we have an isomorphism from B to A, the contravariant Yoneda embedding applied to that f will give us an isomorphism going from home blank A to home blank B, meaning that those two functors are isomorphic in the functor category set C. To show the other direction, going this way, suppose we have some isomorphism I going from home blank A to home blank B. Well then, because we know that y, our embedding, is faithful, which means that all of the home sets get mapped injectively, we know that there can only be one morphism f going from B to A such that y of f is I. There's only one f that gets mapped into our I. And the same is true for I inverse. There's only a single g going from A to B such that y of g is equal to the inverse of I. But then y of f after g is equal to, when we split this up for a contravariant functor, we have to flip the order. So y of g after y of f, which is equal to I inverse after I, which is equal to the identity morphism on home blank A in set superscript C. And the same for the other direction, g after f, we get y of f after y of g, which is equal to I after I inverse, which is equal to the identity morphism on home blank B. But again, we know that this is an embedding, which means it's faithful, which means that the morphisms get mapped injectively. And of course, we know that functors preserve identity. So we have that y1a is 1 home blank A and y1b is 1 home blank B. But then these must be equal because of the injectivity of our embedding y. So we must have that 1a is equal to f after g and 1b is equal to g after f. But then we have that f and g are both invertible by each other, and that means that a and b are isomorphic, which is what we needed to prove for the second result. Finally, let's see how Cayley's theorem can be thought of as a corollary to Yoneda's lemma. So Cayley's theorem is an important and foundational result in group theory, which says that every group can be embedded into a permutation group. And so in order to see this, let's fix some group G. And let's recall that we can view G as a category, maybe call it curly G. And recall that the definition of curly G is that there's only a single object in the category, which is, maybe call it star, some singleton. And we know that the home set from that singleton element to itself consists of all the elements of G as a set. So there's basically one morphism going from star to star for each element in the group G. Let's see what happens if we apply Yoneda's embedding to this category curly G. Well, we need to know that curly G is a small category, but it's small, it can fit in a set. There's the set right there. just a single element. So Yoneda's embedding is going to go from G into the set-valued functors on G. All of the functors going from G into set. What are the objects of G? Well, we just said there's only one of them, star. So y of star is going to give us, by definition, the contravariant home functor with target object star. And if A is a morphism in G, well, then it goes from star to star. And notice that that means it's in home star star, so it's just an element of G. So A is just an element of the group G. And if we apply Yoneda's embedding to that, we get followed by A, which is a natural transformation going from the contravariant home functor to the contravariant home functor, both with only one option, target object star. Let's draw this situation out to understand it a bit better. So we have our category curly G, which for objects just has a single element, which we called star. And then we said that for every element in G, we have one morphism going from star to itself. And so, for example, we need one star, the identity on star, but also we need a unity in the group G, so obviously those correspond. And then say we have some element A in the group G, then we have a morphism for that. Say we have some element B in the group G, then we have a morphism for that, and so on for all the elements of G. Well, now, if we want to look at contravariant home functors, there's only one option. So if we map this by contravariant home functor, well, we can only do home blank star, the contravariant home functor with target object star, because that's the only option. There's only one element. And so if we want to look at natural transformations between contravariant home functors, it's going to have to be between home blank star and itself, the same functor. And so what does it look like on this side? Well, we know that we need one home set for each object in G here, but there's only one element, so there's only one way to fill in this blank, basically. This is home star star. And then for every element in G, which is a morphism here, we do proceed by. That's just the definition of the contravariant home functor. So this is going to be precede by 1 star. This is going to be precede by A, and so on. And we have the same structure down here. Morphisms on home star star. And we know that these are both contravariant home functors, so the natural transformation between them is going to be followed by G for some element G and G. So we're going to fix some element G and G, and then we know that that's going to define a natural transformation going from home blank star to home blank star between the only two possible contravariant home functors, which are each other. This helps us to understand our application of Yoneda's embedding a little bit better. So we see that our singleton element star gets sent to the contravariant home functor home blank star, the only one there is. And if we have any element A of the group G, there's a morphism going from star to star for that element. And there's a natural transformation which corresponds to follow by that element. So Y will send that element to the natural transformation followed by that element. So in this case, Y of A is followed by A. Notice something that's particular about this situation, though, is that if we take one of the natural transformations, say for G and G, lambda G, we know that that's going to consist of a whole bunch of components where each component is just followed by G, but it's on a different home set as a domain. But in this case, we only have one component. There's one component for each object in G, and we only have one element in G. So that means that actually lambda G is just a single set function followed by G, which goes from home star star to home star star. Now remember that within this group, viewed as a category, we have that composition of morphisms A and B is just going to be the group product of A with B. Composition is just multiplication in the group. So in this case, when we say, well, the natural transformation is just a set function which is followed by on G, right? Home star star is G, so it's just followed by applied to the group G. What we really mean is compose on the left with G, and compose on the left means multiply on the left with G. So what we're saying is for any X in our category G, we are mapping it to multiplying on the left with G. Based on this discussion, what we can conclude is that when we map an element A of G by Yoneda's embedding, what we actually get back is a set function going from G to G where we left multiply by A. So that is, we just map an element X to a X where the product is in G. But one thing to notice is that this function, which is just multiplication on the left by a fixed element, is actually bijective. This is a bijection from G onto itself. And so one good exercise to try would be to show that this mapping is actually a bijection. So there's two ways to show that, right? We can show that it's a bijection as a function, which means that it's both injective and surjective, or we can show that it's an isomorphism in the category of sets. That is, we can show that it has an inverse in the category of sets. So then, what do we call a bijection from a set to itself? Well, we call that a permutation. So actually, multiplication on the left by a fixed element is just a permutation on the group G. So what does this tell us? Well, we were looking at the natural transformations going from the contravariant home functor defined on curly G, and we said that the natural transformations between contravariant home functors, where there's only one option, home blank star, is actually a set of set functions where we left multiply by the elements of G. That is, we fix an element I in G, and then we can left multiply any element of G by that element. And we said that this was actually equal to a set of permutations on G. But what does that mean? Well, that means that this is a subset of the symmetric group on G, the set of all permutations on G. And that means that we can embed these using an inclusion map. So an inclusion map just says, hey, if I'm a permutation on G, just pick myself out in this set of all possible permutations. So this might not be all of them, but they're all just going to map to themselves in the set of all possible permutations. So let's just summarize this by putting it directly here. We can say that there is an inclusion map going from the natural transformations on the contravariant home functors, both going with target object star, into the symmetric group on G. Now notice that this is a set of natural transformations between contravariant home functors, and so Yoneda's lemma applies here, and we can say that this is in a bijection with the home set from this target object to this target object, which are the same in this case, both star. And so this is a bijection in the category of sets, that is an isomorphism in the category of sets. But what is home star star? Well, it's just G. So what we've actually shown here is that there's an isomorphism going from G to this set of natural transformations, which is a set of permutations on G, which can then be embedded into the set of all possible permutations, or the group of all possible permutations on G. That is, there's an embedding from G all the way to the permutation group on G, which we get by simply composing this isomorphism with this inclusion map. So this inclusion map is an embedding. It's a trivial embedding. It just embeds itself exactly as it is. And this isomorphism chained together give us an embedding that goes from G to the symmetric group on G, that is the group of all possible permutations of G. And so that proves the final result. And so we've proved all of the corollaries to Yoneda's lemma that we stated at the start of the video. So we'll call that QED. Just one more quick thing to note here is that sometimes Cayley's theorem is phrased as every group is isomorphic to a subgroup of the symmetric group on that group. So in this case, we can see that these natural transformations, which are a set of permutations on G, are a subset of these permutations, and they're isomorphic to a group. That is, they're actually a subgroup of S of G, so the symmetric group of G. So we can see that both statements can be proved using Yoneda's lemma. Another good exercise to try would be to look at these functions here, multiply on the left by A, which we know is a bijection and therefore a permutation from G into G. So what we might ask ourselves is this a group homomorphism? It's going from a group to itself, but is it a group homomorphism and therefore a group automorphism or not? And we might ask ourselves the question, is it always for all values of A? Is it never for all values of A? Or does it depend on the value of A to know whether or not this is a group homomorphism?